In this video, we are going to talk about how we can use the second derivative, which we are slightly more familiar with now, to do more than just examine concavity and inflection points. So while it is very useful for seeing whether a graph is concave up, concave down, and then where that changes, we can also use the second derivative to tell us where you have local minima and maxima on your original function. So while we've already learned a test that does that, so their first derivative test allows us to do that, and it allows us to determine whether your original function is local extrema by examining the sign changes of the first derivative. But sometimes we aren't given enough information about our original function or our first derivative to determine local minimum and maximum points this way. And so we have another test that also allows us to do this. So don't want you to get confused. Both your first and second derivative tests provide information. Oops. About extrema. So they provide information about your local or relative maximum and minimum points. What we did in the last video was we're just examining concavity using the second derivative. It doesn't have a name or anything like that. So both of the formal tests that we use, both your first derivative test and your second derivative test, tell us information about extrema. So we know the first derivative test allows us to make a sign chart and then determine whether or not our original function has a max or a min based off of whether it changes from positive to negative or negative to positive. What the second derivative test allows us to determine is whether or not you have a max or a min by examining the concavity. I'll kind of show you how this works. So suppose C is a critical point of the twice differentiable function f of x. So that just means you can take the derivative twice. So C is a critical point, which means that either your slope does not exist or equals 0, or excuse me, your first derivative equals 0 or does not exist. So yes, the slope. What we know is that if your second derivative is negative at that critical point, then our original function would have a relative maximum at C, and I want to talk about why. So if our second derivative is negative, that means our graph at that C value, so on our graph at that C value, it would have to be concave down. And so if you have a critical point and you have it concave down, there is no way that can be anything else except for a local maximum, right? It's a critical point because your first derivative equals 0, and I know at that value that my graph is concave down because my second derivative is negative. If your second derivative is positive, so if we went the other way, but we know we have a critical point, so I know that here I have a point where my tangent line, my horizontal tangent line is there, and so it has a slope of 0, and I know that at C, my second derivative is positive, well, that means my original function has to be concave up, which means that I would have to have a relative minimum there. So it's kind of the combination of the fact that we know C is a critical point, so you know that there has to be a horizontal tangent line there, and then just whether or not it's concave up or concave down. Now, the only downfall to the second derivative test, which is why it isn't used as often, is if you find that at your second derivative, we have it equal to 0 at that critical point, then no conclusion can be made. So there might be a maximum there might be a minimum there, or nothing could be there. So the important information is if you have a critical point and they tell you it's a critical point, or you find that it's a critical point, and then you know your second derivative is positive or negative there, you can make a conclusion about it. It either has a relative max or a relative min. However, if you find that your first derivative is 0, which means there's a critical point, and your second derivative is 0, you have to go try something else. Nothing can be confirmed from this last part. So like I said, the second derivative test doesn't pop up as often, but you can sometimes classify your critical numbers or your critical points of your functions using the second derivative. So we're going to try it here. So you were going to use the second derivative test to classify the critical numbers of this original function, which means we need to find our critical numbers first. So to find critical numbers, we find our first derivative, we set it equal to 0, so let's find our first derivative first, x cubed minus 6x squared. We set it equal to 0, so we get 3x squared minus, nope, I'm taking a derivative unnecessarily. Okay, so there's our factored form. And then we find our solution. So x equals 0 is a critical number and x equals 6 is a critical number. And so now I can use my second derivative test to try to classify these critical numbers. So what I'm going to do is I'm going to plug those, I'm going to find my second derivative, which would be 3x squared minus 12x. And I'm just going to plug those in and see whether or not I get out positive or negative numbers. So if I plug in, so if I do y prime of 0, I get 0. So this is one of the circumstances that falls into this last category. No conclusion can be made. So no conclusion. We'll have to revert back to our first derivative test. Okay, but y double prime of 6, if I plug that in, let's see, you get 3 times 36 minus 12 times 6. So let's see, what's that? 90 plus 18. So 108 minus 72, which will end up being a positive number. It doesn't actually matter what number it is. So it's a positive number. So I know by my second derivative test, since 6 was a critical point, or a critical number, excuse me, and my second derivative is positive, that means that on my graph, oops, at 6, I had a critical number, so I had a horizontal tangent line there, and my second derivative was positive, horizontal tangent line, which means that my graph was shaped like this because it means my original function was concave up. I would have at 6 a minimum. So we would say x equals 6, or at x equals 6. There is a local min. And then you can say because x equals 6 is a critical number and y double prime of 6 is positive. Okay. We weren't able to tell anything about 0 at in using our second derivative test. So this would be, in this scenario, you could revert back to your first derivative test. So for example, I could make a sign chart, and then I could do 0 and 6, and then I could test values in my first derivative. So if I tested, for example, we could test -1, so I'd get a positive and a negative, so negative. And then if I tested 1, I can plug in 1, get a positive, 1, get a negative, so that's still negative. And so at 0, I would have a saddle point, and that's why we couldn't make any conclusions using our second derivative test, because our we didn't result in a max or a min because your second derivative wasn't positive or negative when I plugged in 0. And so sometimes that'll result in a saddle point, sometimes it won't, but that's why it didn't work for y or x equals 0. Okay, so we'll work more with this and we'll practice this more, but I just wanted to give you an example of it and kind of talk through it.